Good afternoon once again, and welcome back to our Signal Innovation Showcase series. I'm George Seifers with Signal Magazine. We are now about to be joined by Evan Pilecki, who is going to talk about the intersection between cybersecurity, quantum, and, I'm sorry, what?
Security.
Security.
Yep.
Sorry.
Excellent.
I
Thank
thought
you.
you said something too.
Oh, no, you're good. Good afternoon, everybody. Again, my name is Evan Pilecki. I'm the Senior Product Manager here at Thales TCT. So I'm responsible for all of our cryptographic key management portfolio. So that includes our hardware security modules, as well as our key management and data encryption platform, CipherTrust. So who we are at Thales TCT, a little bit about us. So we are a proxy entity within the larger Thales global parent company. So we fall under Thales Defense and Security Incorporated. We service the U.S. federal government exclusively, so all of our products are designed and developed to meet U.S. federal need, and we are protected by a proxy agreement as well as a national security agreement with the CFIUS committee to ensure that we can provide secure products into the U.S. federal government. We're located up the road in Abingdon, Maryland, and we have a bunch of cleared folks to help you as U.S. federal government customers deploy solutions as needed. So what we're talking about today, so artificial intelligence and quantum computing, we see as converging technologies that independently pose an existential cybersecurity risk, and both at unpredictable pace. So these are important technologies that we see sort of emerging and converging at the same time, which have significant security ramifications, which we'll be talking about today. So just a little bit of baselining for folks who might not be familiar with the various technologies at play. So dumbing down artificial intelligence a little bit, it is a sort of nested group of different technologies down from sort of the broader artificial intelligence as a whole, which covers a whole different gamut of technologies from, it can cover automation processes to, as we'll sort of narrow down into machine learning processes. So this is utilizing recursive computer processing and learning techniques to detect patterns in different data sets. And that within that is deep learning. So this is using large quantities of data sets to do high-level understanding of that data in order to do processing and actions against it. Within that is the field of generative artificial intelligence, which large language models, as I think we're all familiar with, as products that we use, that many of us are using day to day, fall within, right? So it's a very sort of Russian nesting doll scope of technology to get down into, when we talk about AI, down to large language models and how that's actually impacting users on day to day. On the quantum side, we typically group quantum technology into these four main areas. So you have the broader quantum computing, which is the utilization of quantum computers, like you see IBM demonstrating today, to do complex computations that cannot be achieved by a classical computer platform. The next is quantum key distribution. So this is a distinct technology from quantum computing. This is utilizing the inherent physics in quantum mechanics to securely distribute keys across different endpoints. Then there's quantum random number generation. So this is, again, leveraging the physics of quantum, not to do computational efforts, but to generate randomness and derive random numbers through quantum entanglement of measuring how typically photons sort of interact with a sensor. And then finally, there's post-quantum cryptography. So that's sort of the main thrust of when people are talking about and concerned about quantum today, they're concerned about a quantum computer being able to impact and threaten classical cryptography and therefore risks all of the data protections that we've built up over the last 30 years. So as we take a roadmap view of the discussion today, I'll be first talking about sort of the positive, right? What does artificial intelligence and quantum computer give us as a benefit to cybersecurity? Then what are sort of the risks and ramifications of these technologies being used by malicious actors? And then finally, how do we approach then protecting our data and our artificial intelligence models against those malicious actions? So first, the positive, right? So McKinsey, the consulting firm, recently published a study where they looked at what is the computational investment going to be across both human users as well as artificial intelligence systems over the next, through 2030, which is a key date, right? So if you look at sort of CNSA 2.0 requirements around post-quantum cryptography, 2030 is a key deadline for migrating to post-quantum cryptographic systems. And so you see sort of this convergence of timeline about when McKinsey is estimating that essentially at a 3-to-1 capacity, artificial intelligence systems will be consuming computational resources against human users. So you see a really big gap and development of artificial intelligence systems expected over that timeline to grow and quickly outpace what the total capacity of human users on computer systems are doing. So what specifically can LLMs give us? When we look at cybersecurity and the principles of secure design, what does it look like to enable and employ artificial intelligence systems to ensure that software that we are delivering out to customers is itself secure before it even leaves the factory, right? So LLMs are a great tool for our developers because it can take care of a lot of the initial and low-hanging fruit and initial structure of deploying code out into the field, right? So you sort of employ an LLM to draft code for you, and then it gives the actual developers time, the human developers, time to focus in on what is the security then of those programs and the functionality that we need within them. And so it's a really great tool to sort of free up development resources to then focus in on security of the products themselves. The next is AI tools right now are great to scrub code. So as code is being written and about to be released, right, you can employ AI tools to go and scrub the code for vulnerabilities. It's a great check as part of the quality assurance processes before any sort of software is deployed out and released into production. Those tools are great for doing that initial scrubbing of code. Eventually, we don't see this quite yet, the expectation is that AI systems will be a valuable tool in doing automated red teaming of software before it leaves, right? So right now we can sort of scrub the code at a surface level for expected vulnerabilities within how the code is written, but we expect AI systems to eventually be able to take running code and do red teaming against it in an automated fashion, to really get in and attempt different exploitation of software to ensure that any exploitations that an AI system can affect, that developers are able to then correct and patch before software is released. So it'll be a really great asset and tool as part of the secure by design effort for software development into the future. And then once software itself is deployed, AI tools will be a great boon to sort of the heuristics-based intrusion detection and reaction, right? So AI systems, as we sort of talked about in like the Russian nesting egg, right? It's a subset of deep learning technology. These systems are great at interpreting large data that a human user itself could never go through. So the idea is that an AI system will be able to get an understanding of how the heuristics of a network and be able to detect anomalies and react to them much more quickly than a human user is able to do today. And then as part of the reaction then to expected malicious activity, we expect to see AI systems be a great research assistant to our intelligence analysts who are trying to figure out and determine attribution or figure out what actually happened on the network. If you can employ a whole bunch of artificially intelligent agents to go collect the information and synthesize it for the human analyst, it should really accelerate and make more pristine the information that decision makers are working with. And then when you look at sort of what are the benefits expected out of quantum technology will enhance security over time, right? So sort of the two things we talked about at the top, right? So quantum key distribution, this right now is an expensive technology, but over time it is expected that investments and development of quantum key distribution will make it more cost-effective and feasible to deploy on wide scale. So this will greatly impact and help ensure the integrity of cryptographic keys as they are being distributed across the network. And then we have quantum random number generation. This is available today in lots of different technologies. So this is enabling alternate sources of entropy. So that is the randomness at which cryptographic systems use to derive keys, right? So secure keys, cryptographic keys are only as secure as the randomness from which their entropy is sourced. And quantum physics are a great source of, some would say perfect, if not near perfect, source of randomness and entropy for those cryptographic systems. So then turning to some of the threats then posed by both AI and quantum computing, right? So this very much reflects sort of the positive if we look at AI systems and what they'll enable within malicious actors, right? So AI systems and LLMs will essentially raise the baseline of when you're looking at the hierarchy of malicious actors, and script kiddies being sort of the lowest hanging, right? They're just sort of jamming out basic code. We'll give them access to an LLM, and now the baseline competence of all malicious actors is expected to rise, and therefore the need to defend against them now becomes that much greater because you have a much more competent adversary that is operating on the network. Next up is social engineering. Becomes much easier when you're trying to cross language and cultural barriers, right? So if you are, say, a cyber criminal in North Korea trying to influence and attack, U.S.-based interests with an LLM that is trained to speak in plain English and understands through its learning the cultural values and expectations of a United States user. Now you have an operator operating overseas that is now able to send much more convincing phishing emails or perform deep fakes of both video and audio of what a U.S. user would expect and react to in terms of social engineering and impact. And then similar to how we expect to be able to benefit from the red teaming capabilities of an AI system, right, that quickly turns into malicious activity that can then be automated on a 24/7 basis and sort of an army of robots then able to attack systems once they are able to achieve the ability to execute malicious acts that outpace and outperform basic human users and our ability to then anticipate those attacks. And then quantum computing is sort of we talk about 0 day, PQ 0 day, right? What happens when a cryptographically relevant computer is developed such that it is able to break public key cryptography? Right, public key cryptography is the basis of essentially all security on the internet today. That is how your credentials are derived through your badge and company, like CACs and PIV. That's all PKI-based public key credentials, all internet-based encryption, right? Communicating to your bank over the internet, that is all done on the basis of public key cryptography. And a cryptographically relevant computer will break that cryptography. So this is sort of a known quantity. When I sort of look at and compare quantum technology versus AI, I see them sort of as an inverse risk, right? So quantum technology, we know exactly what the risk is, right? Classical cryptography, classical public key cryptography will break. It's just an understanding of when will that happen, right? What is the rate at which adversaries who wish to utilize that technology are deploying it and able to effectuate those threats? When it comes to artificial intelligence, we sort of have a great understanding of how quickly that technology is accelerating, but the inherent risk in that technology is less clear, right? So we don't know if the good will outpace the bad when it comes to artificial intelligence, but we have a great understanding of sort of how that technology is progressing over time. So they're a little bit of an inverse problem when you're looking at time versus risk and the potential impact. And when looking at quantum computing, right, what happens when public key cryptography is broken? These are sort of the highest risk items, right? Once you're able to break classical cryptography and PKI, that means that it becomes much more easier to forge things that are being done utilizing those credentials, right? So any contract you sign, any electronic signature you perform is backed by a PKI, right, a public key cryptography. And if you're able to forge those signatures, that puts the integrity of pretty much any contract that has been digitally signed at risk, right? You can modify the contracts and reapply the same signature because now you have access to private keys. And it becomes no longer can you trust digital signatures. Digital signatures are the basis at which firmware and software is securely deployed and updates, right? So every Windows update, every firmware update in field to a piece of technology is all backed by public key cryptography. So once that becomes broken by a quantum computer, the inherent risk in systems trusting updates that are coming to them and those updates being malicious in nature skyrockets, and it becomes very hard to trust any updates coming into systems that are not quantum resistant in nature. You're able to effectuate man-in-the-middle attacks, right? So if all of the foundations of security on the internet are broken, right, I, as a malicious actor, can go in and very easily get access to and trace all communications happening across the network. So command and control systems that are communicating over open networks, right, that are right now protected by classical cryptography, CNSA 1.0 cryptography, that will become inherently at risk. And so all of those communications are then put at risk, which sort of leads into the harvest now, decrypt later scenario, right? So an adversary sort of hoovering up all the information that is being transacted across the network now, and at a later date, banking on the fact that they will have a quantum computer able to decrypt that information later. So if you think about state secrets that are being transmitted across the internet today, being protected by classical cryptography, and someone collecting that information now, and that information is expected to be protected for 50 years from now, but in 5 years, someone has a quantum computer able to crack and decrypt and therefore read classified or state secret information. Now they have access to all that information. So it becomes imperative then to accelerate the pace at which we are treating quantum resistance, and that is why you see agencies like NSA push CNSA 2.0 requirements on such an accelerated pace as compared to older transitions across different versions of cryptography. Right, and then sort of the catastrophe is what happens when I have an AI army of robots that with malicious intent that have access to a cryptographic relevant quantum computer, and now have essentially, I have a whole army of automated robots able to crack and break and gain access to all protected information. And sort of, this is sort of the worst case scenario, right, of these two technologies converging in the worst sort of way. So how do we protect that technology, right? So when you're looking at AI models, they're sort of broken up into three different parts, right? There's the inputs to the model, there's the model itself, and then there's the outputs from the model. I'm not going to walk through all of these, but you can see there's sort of different unique threats to AI models across those three sort of areas and components of the system. And it becomes critical then to treat them in kind and make sure that you're protecting across all three areas. So looking at the data itself then, that data that the models are using at rest, in transit, and in use, there are a lot of different ways at which you can go after that problem, right? Looking at how do you ensure that the data that is being utilized to train the model is classified appropriately and protected, that data is encrypted to ensure that only those with proper access to that information has access, and then proper tokenization and masking. So this is taking, PII or financial information, that sensitive information, and making sure that it's obfuscated appropriately within those systems, even as they're stored encrypted, so that only those who need to know that information have access to it, and it's properly obfuscated, even while it's being processed through the system. And then while data is in transit, right, you want to make sure that you are monitoring all of the transactions that are happening across the network, and you are employing tools that allow you to do that monitoring and detect any malicious activity that might be trying to gain access to any of this data. Again, you want that data encrypted across the network as it's moving. And then while data is in use, right, you want access to behavioral analytic tools so that you, as the administrator of an AI model system, understand how that data is being utilized in real time. Then you want to make sure that you have the authentication and strong authentication technology in place to ensure that access is appropriately controlled. And you want to employ confidential computing. So this is newer technology that is available that allows you to isolate within the CPUs of systems that are utilizing these technologies, the different workloads to really isolate and protect those systems while they're in use. And then finally, how do we sort of go after the quantum threat? And that's a whole process here that starts with sort of cryptographically inventorying and understanding what cryptography you're using across the network, ensuring that you have PQC test environments in place so that you understand how those systems need to be transitioned, right? Prioritizing your data from the most critical, right? We talked a little bit earlier about state secrets and stuff that has to be protected for a long period of time, and prioritizing that most critical information with the mind that someone is collecting that information now and expecting to be able to decrypt it later. Practicing crypto agility. So this is employing and not making your systems sort of hardwired to particular types of cryptography, right? Without going too deep into the post-quantum cryptography sort of dynamics, a lot of those algorithms are new and there was a whole selection process over the last few years. They've been validated, tested, and standardized, but again, that's new technology, and we're not quite sure how that will stand up to a quantum computer. We have pretty high confidence, right, of quantum resistance, but there's not 100% assurity, so we need to make sure that our systems are able to be agile as they're deployed in case a turn needs to happen at a later date. And then you want to then implement, right? So you want to do the transition in accordance with requirements like CNSA 2.0 if you have systems that are required to comply there, and then just generally take, right, CNSA 2.0 as probably a good benchmark for all of the systems that are being deployed as a timeline and expectation of risk when it comes to quantum computers. I think I have maybe a minute in time for one question if there is.
I got a question.
Sure.
So, and I'm relatively new to this, so excuse me, it sounds like you're probably.
Yeah.
You say that there is, estimated probability of success against future cryptography, with these standards. Like, isn't that like known to the adversary, right? Like, so if they're developing their quantum technology, they know what they're doing. It's quantum proof, and they can. You're like, isn't it kind of still looking nice to themselves?
Yeah, so for those, just to repeat the question real quick, the question, which you can correct me to summarize, right, is we have adversaries who, right, out in the open, we are developing these post-quantum cryptography standards, right, the NIST, they are published standards out through NIST, and the question is, right, if we have adversaries who understand what we're doing, isn't there value in sort of defense through obfuscation, and why are we sort of approaching this out in the open and giving sort of the adversary a leg up in the algorithms that we're selecting? That work is like, for I would say the last several decades, right, the actual algorithms selected have been public knowledge, right? You look at CNSA 1.0 and those requirements, everyone sort of understands that we're deploying AES, RSA, right? All the commercial algorithms that we understand have been widely known. It's in the security of the algorithm itself, not in the selection of which algorithm you're using, right? For other systems, right, there's a whole world of type 1 classified algorithms that the federal government uses to protect their own systems. That's not what we're talking about here, right? So that is sort of obfuscation of what are those cryptographic systems doing? We don't know because they're classified. When you're looking at sort of what are the commercial solutions available, that sort of needs to be done in the open because everyone needs to know and understand what they're developing to. And the security is not inherent in not knowing what those algorithms are. It's in that we trust the mathematics of the algorithms themselves. Yep. Thank you, everybody.
Evan, thank you so much. That was great. Thank you all for being here once again. Our next presentation in 10 minutes is the one that we should have heard yesterday before somebody got cute with the fire alarm. So come back and join us for that one.